You can start, Imre, please.
Thank you so much. In this second lecture today, first of all, I would like to reflect on the takeaway or the positive takeaway of the first lecture. What is important for us to see here that we are trying to learn about the future cyber-physical system. We have to see what this future can be, because if it is not seen, then it is very difficult for researchers and also for developers to take the necessary steps. And I hope that this presentation, which comes now, which will discuss two examples for experimental smart cyber physical systems, will show you that what can be the first step in this direction and how we interpreted it. Actually, what before going into the discussion of the systems, let me tell you that the goal of this presentation is discuss two application examples, two prototype systems which we developed for particular applications. These applications are social and human and not directly heavy industrial applications. These were developed in the framework of PhD project. Actually, this book, what most probably you can see now, and this other book, what I show you now through the camera, are the content material concerning the development and the description of these two systems, what I'm talking about. So, as I mentioned, they are exposing successful coupling of the social demands and the technological affordances. And the end result of these projects were testable first prototypes, not more, not less. And obviously, here it has to be seen that full-scale development of cyber-physical system requires a lot of effort. For this reason, it is not about a complex and complex cyber-physical system. What was implemented for the demonstration purposes, it is much more a node, a actor node of that particular system, which can be replicated, multiple of them can be developed, and they can be connected, and this way they can form a comprehensive cyber-physical system, or if these systems are connected, even a system of systems. The two prototype systems, what I will present, serve first of all for the purpose of demonstration of feasibility of brand new concepts, and the second one is that they may trigger or at least support learning new opportunities towards similar enhanced solutions. So within my research group, which was dedicated to cognitive engineering of cyber-physical systems, we conceptualized several systems and worked out several systems up to the demonstratable level. One of them was a system for engagement enhancement in stroke rehabilitation. The second project was about facilitation of indoor fire evacuation. A third project, which is also remarkable, was a system for fault prevention in urban and rooftop greenhouses. In addition to that, 6 more demonstrative systems have been prototyped. For instance, additional one, just to mention one example from the 6, one was developed for supporting the coaching of table tennis players. Obviously, here in the Netherlands, we don't have sufficient number of trainers, and for this reason, the idea came up that to have a cyber physical system as a trainer for these table tennis players. So these are just examples. The first application case that what I mentioned was the engagement monitoring and enhancement system. This is the work, and I'm very grateful and proud of him, the work of Chong Li from the China, from the Tsinghua University, and we published a lot, and we are still contact. So his original topic was the research into cyber physical engagement and how to enhance engagement in the field of stroke rehabilitation. Most probably know that stroke is a frequently occurring sickness. It needs long-term rehabilitation therapy, and on the other hand, a number of the total number of physical therapists who are available for this is very limited, and the quality of the instrumental rehabilitation cannot be guaranteed, and it is also scientifically proven that a deeper involvement of the patient in the rehabilitation process improves the outcome, improves the result. So before going into the development, obviously we studied what sort of traditional approaches were out there for the rehabilitation, and they were very complex, if not complicated, robotics application. And they have developed and programmed for a particular functionality. They typically feature limited adaptation and lack of any reasoning. So they were just pre-programmed, as I mentioned, for the task. And obviously, the comfort and experience of the users was not at that level that it could have been expected. And it was difficult to adjust them to the very needs of the patient. And more importantly, they didn't monitor or enhance the engagement of the patient in a smart manner. Because, as I mentioned, if the patient shows a higher level of engagement, the rehabilitation results will be much more effective. And for this reason, the role of the cyber physical system is large to contribute to the engagement of the patient. Later on, I will show you how we achieved it. So the objective of the research and development work to develop an overall model of the therapeutic engagement. And we developed this model. I just show it without going into the technical details. You can download even the PhD from the repository of the Delft University of Technology. And if you are interested, you can read it. And then we said that as a kind of pragmatic objective, concentrate on the software and the cyberware constituents, because they are more interesting perhaps than the physical things here. And based on this, we focused on that sort of interest domain, which is surrounded by the baseline, and actually it has a smaller part of the physical part and larger attention on the cyber part. So as a beginning, we started studying the influential factors, and we identified that actually four major fields of the influential factors could be identified: the motor, the perceptive, the cognitive, and the emotional influential factors. And these four sets were taken into consideration in the further work. We dealt with the motor, the perceptive, the cognitive, and the emotional factors of enhancing the patient engagement of the process. So if I want to give you more insight in this, then I have to mention that actually this motor, the perceptive, emotional, and cognitive domains of engagement monitoring and enhancing are interconnected. And this is how we have to take into consideration that not only one of them, but all of them had to be addressed in a kind of harmony. Based on this consideration, we ideated an architecture which consisted of a assistive robotic subsystem. Immediately I will show you. And then we had a engagement monitoring subsystem, which was on the cyber part. We had a gamification subsystem. Obviously, you can imagine that it is related to the cognitive issues. We had a smart learning subsystem, and we had a engagement enhancement subsystem here. So the physical part and the cyber part has been defined like this. And then, obviously, we try to follow what is typically known for the architecting of cyber physical system related to the control in a follow-up presentation. I will mention the 5C model. So we actually adopted this 5C model, which identifies a hardware layer, a software layer, a cyberware layer, and service layer in our interpretation. And we mainly use the MATLAB for implementing the elements of the software. The cyberware obviously included learned content and formalized knowledge, and the service was what the patient received. So this is the overall architecture of the system. I mentioned that we had a limited attention on the physical part, but for the reason that we try to demonstrate the applicability of this type of system for upper limb rehabilitation and not other things. For this reason, we selected a electromechanical system and implemented a electromechanical system. You can see the image here, which actually was the robotic or robotized part of the cyber physical system. Multiple units can be set up, and multiple people can exercise with them at the same time. Actually, every one of them is an actual node, and it is managed and controlled by the cyber part. Various monitoring devices were used. For instance, the Mayo device, most probably you know it, the I-type device, the emotive epoch design, and the InfoSight equipment also. So for face analytics, this is what we used as monitoring devices. And the software and the cyberware constituents were formed the following way. I already showed you the image about the physical part. And then we had a subsystem which was monitoring the motor engagement, namely the activity of the motion of the human hands, velocity, for instance, and the forces exerted by the muscles were detected by the equipment what I mentioned beforehand and were sent to the processor unit. In addition to have, we had the gaze observation. This is the perceptive part. So we monitored the eye of the patient if they are really paying attention to the things what they were supposed to do. Then we also measure the cognitive reactions. We also use brain-computer interface, and we express it formally. developed kind of data streams for that. And then also we try to monitor the emotional state of the person, and we use face recognition and machine learning here to compare what was observed on the face with typical models which we had for the various emotional stages. So this is how the system was conceptualized. And obviously, it was very important to mimic with the system the awareness building and operationalization the awareness. So we used the detected signals as situation indicators, the 4-1, what I mentioned beforehand, and we tried to develop a kind of runtime usable model based on that. Obviously, this is a problem, what is typically an open control problem. You don't know what is expected because it cannot be predicted for the reason that every patient behaves differently for the treatment or based on the treatment, and their engagement is also individual, so you cannot have a standard there. For this reason, any model which is a kind of static and predictive model is useless. We had to create a model which was actually activated runtime, and based on this runtime activation, we could get control information out there. So as you can see here, this simple, relatively simple, because we know already that it could be enhanced and improved from many ways. So this simple model, which includes the motor, the perceptive, the cognitive, and the emotional axis as dimension of influence, the engagement in the process, this was the basis. We didn't have a default value, we didn't have a threshold value, we didn't have a ceiling value, we just had a starting value as I explained here. So we have a smart learning mechanism, and it combined the motor, the sensor, the cognitive challenge results, and try to develop an indicator for how much the patient in treatment was aware of what is happening, what he has to do, and how he has to do it, or he has to do it. So here is the principle or the explanation on the principle of the data-driven operation. Obviously, the physical part had a role in that, because with this handle, when it was called by the patient and moved, we could measure the intensity of the work, we could measure the force and the resistance, and so on and so on. And all these pieces of information, what you can see here, and I explained beforehand, was put into a kind of meta model, a control model, a runtime developed model, which served for the purpose of reasoning as well as for control. So here are the 4 axes, what I already mentioned beforehand. And then I mentioned to you that there was no default value. We just, when we started the measurement, when we started the exercise, we had a starting situation, and it was recording with regards to the values obtained in the motor, in the perceptive, in the cognitive, and the emotional domain. And then there was a progress when the patient went further the exercises. Then we observed other status, for instance, a attending situation in which it went to the perception domain, and extreme attention was given to the perceptive thing. So more focus was given, what was projected for the patient. And then we also had more balanced situation, for instance, when the emotional aspect, the motor aspect, and the cognitive aspects were much more balanced. And this was the goal. And whenever we went to the extreme, we tried to change something in the system in order to come back to a more balanced situation. And actually, this balanced situation, when it was achieved, this balanced situation is so much contextualized, it's so much situated that actually couldn't be formulated in advance. Even our consultations with doctors couldn't help us to mention that what a balanced situation, or couldn't explain what a balanced situation was for the different patients. But it's fine. It had to be accepted as a kind of explainability restriction. But on the other hand, whenever the system detected a kind of approaching to or achieving a balanced situation, then we knew that the patient had sufficient engagement, and then the task from that moment onward was just to keep up that particular level of the engagement. So this is how it is working. This was purely based on data, and actually the integration of everything came from the data. In my presentation, you will see diagrams, for instance, that how we process the knowledge internally. This is a scheme. In the PhD thesis, you can have a much more detailed explanation on this particular issue. The computational methods were also challenging. So actually, we wanted to have a learning mechanism, and we considered regression, and we also considered classification in many places, and we tried back propagation neural network, probabilistic neural network, multi-layer perception network, support vector machines, memory-based classifiers, deep reinforced learning mechanism, and so on and so on. And the experience with them, because the implementation of the reasoning was not so easy. So artificial neural networks and naive-based were extensively tested because they were candidates as reasonable mechanism for learning and reasoning with the system. Interestingly, we found that naive-based reasoning was more effective than the neural network type of approach in this particular situation. The data sources are here. You can see what sort of data were and signals were extracted through the devices. What we use here, the devices are mentioned, and these are the different signals, and they were related to the four aspects of the engagement, and finally the synthesized data for something about the engagement as a whole. And obviously, these sort of recordings were made in the different exercises concerning the different aspects. This is just an example to show you. For the cognitive engagement, we use different games. These were projected on the screen, and obviously solving the cognitive challenge was an indicator of the cognitive engagement of the person, and paying attention to the details which were out there were indicators of the perceptive engagement. And then we implemented, this is what you can see here, the implementation of the cyber-physical based and engagement monitoring and enhancement setup. Obviously, this is just one node, and this is something what you can develop in a university environment. I am anyway here is strong. So if it goes to a industrial company, most probably very soon it will have a much more attractive, sophisticated shape. But for us, 4 years were there, and we were not talking about the commercial values, but about aggregating knowledge related to this particular system. Here you can see the engagement assessment part. This is the tracking exercise. These are the measures in the equipment. What we use then here is, for instance, the video game exercise in real life. So this is the overall image. This is the outcome of this work. And then you may study several papers what we published. First of all, the PhD thesis, which has the title Cyberware Solution for Engagement Enhancing Rehabilitation System. We also published this paper, which is titled Development of Engagement Evaluation Method and Learning Mechanism in an Engagement Enhancing Rehabilitation System. This was an early exercise in 2016. Then we published something on the implementation concept. This paper is about that, and this was a paper which reported on putting the robotic upper limb rehabilitation system into practical usage and investigating the achievable engagement level. So this is the end of this particular presentation. I stop for a moment with it, and if you have questions, whatever type of questions, please be so kind to share it with me.
Any
Do you
questions?
have any questions, please?
Any questions from participants?
Sorry?
No. It seems no questions.
Yeah. No problem. Then I believe the best is then if I just continue with the second block here, which is about the second prototype system what we have developed. I hope that you will find it interesting. I believe it is a completely different attention field and a completely different approach, but also something what those who really want to deal with next generation cyber physical system should be aware of. So let's share the screen again. And I believe the recording is going on. So I come back to the second part of the presentation. Actually, this is the fourth block today, which is about a other demonstrative application, a prototype informing system for indoor fire evacuation. So please see here the difference between the cyber physical system and connect it to my explanation what I provided earlier. So the goal of the previous system was providing services. The goal of this particular prototype system is providing information in a particular situation, which is a fire evacuation from a, let's say, a high-rise building. Let's see what it is all about. Let me summarize our assumptions first. The first assumption was that preventing disastrous fires and similar catastrophes in the concept of the smart cities needs attention. So this system development actually is somewhat, not directly, but indirectly related to the smart city. So management, and the second assumption was that the management of indoor building fire is of high importance in the case, or is of the highest importance in high-rise buildings, because then the damage can be serious and many lives might be violated or in danger. It needs a continuous monitoring, real-time alarming, context-sensitive decision-making, and informing. This was the third major assumption. And these are all functions, as you can recall it, of cyber-physical systems. The two major technological challenges were dynamic context processing, because the fire was had to be supposed to proliferating, and the people are running up and down, and the building parts or whatever may collapse or becoming dangerous. And obviously, what we saw that the people should be informed somehow what to do in this situation, because otherwise they start panicking. And the assumption was that everybody or most of the people did have a mobile phone, simple mobile phone, like myself with them, and if they saw people who didn't have mobile phones, so they were not detected using their mobile phone. They could be directly informed by those people who had phones. So the cyber-physical informing system functionality had to include, for instance, situation analysis, what's going on the floor, message generation, and message distribution to the people. That's what we had to implement. And as I mentioned, smartphones were assumed to be the nodes, and the devices, actually, if you consider it from the IoT perspective, the user nodes and devices in this ad hoc networking and communication, because obviously the networking had to be created ad hoc, not a pre-planned manner, depending on who the people were there and what they did. So here is a visual image of what we are talking about. A building in which a fire is started, and the people try to escape. Obviously, if they are not aware of the dangers, and if they are not behaving in a kind of disciplined way, it may be disastrous, We can assume that the firefighters can be informed and they will come, but this is also just one aspect of the operation of the cyber physical system. I mean, informing the firefighters about this. And let me show you the general architecture and the operation flow of this system. So we assume that there are time-varying physical objects and processes in the physical domain. And then we have a computational engine, which is assembling and processing and availing the information obtained through a sensor network. And first of all, this computational engine has a dynamic context handling mechanism, which is a genuine invention, actually, we have created. And then this is connected to a situation awareness building mechanism, which builds a dynamic awareness of the changes of the situation. Then there is another part of the computational engine which derives a evacuation plan, and it has a reasoning mechanism dedicated for that. And this reasoning mechanism is obviously application dependent, but not but must be independent of the situation. And then we have a fourth part of the computational engine, which is about message generating and sending the messages to the people who were involved. So the actuators and the effectors here are informing terminals. And then obviously the computation and reasoning happens in the cycles because every minute, as I said, the situation may change. Even a second fire may burst out from there and it has to be monitored. Now, I mentioned the importance of the context information. Let me elaborate a little bit on the context information, actually what it means in our context. We identified different primary sets of context information. For instance, identity information, name, ID, existence. These were allocated to the entities which were included in the situation. The spatial context information, the surroundings, the location of the individuals or the thing, the distance between the things, and so on and so on. Then the temporal aspect, the moment in time when something happens, the duration, season, and so on and so on, and attributed information, for instance, what sort of material, color, property, and so on had to be processed. Then the secondary, there was a secondary set of context information defined, for instance, as activity, what the people did, what sort of tasks they did, what sort of actions were busy with, what sort of behavior they showed, because this was element of the evacuation strategy planning, and what sort of factors influence it. For instance, the belonging to different classes of entities, the dependence, someone. For instance, just consider if one of the people to evacuate is a blind person. It is immediately a context information and a strong dependence relationship and factors what should be taken into consideration. But obviously the information about this sort of thing should be detected and belonging also here. The design, the application, the user, and the resources and so on. And the fact there was a third set of context information defined by us, which is called the intentional category, the objective of the whole, the roles, the beliefs, the, for instance, who the role says that who obey to whom. For instance, just consider the fire, if the firefighter says something or a similar people or the people in a similar role carry something. So these were the things here. And then as you can see, these three categories of context information when done from the concrete and explicit to the abstract and implicit. For instance, the roles and the beliefs of the people that, okay, I will not be suffering from the fire or whatever. These are all pieces of context, intentional context information. So this is the information in general, what we process, and obviously here the relationship management had a important things, and we just found out that the core concept here is the distance. Distance, for instance, in a sense that how far the people are from the fire, how far the people are close to each other, because, for instance, when they are very close to each other, they may block the motion of the other people, and so on and so on. So this is how we came up with the idea of the chessboard, because here everything is defined by the distance. So if something is standing here, depending on knowing what that particular entity is, you can forecast a lot of alternative strategies or a lot of alternative moves. This is how it was recognized by us, and this is the fundamental principle of developing our strategy. So the relative momentary distance was used as a contextual basis of semantic reasoning and decision making in our prototype system. So we converted in this conceptual scheme into what we call the spatial feature representation matrix, and it had different domains. For instance, it had the persons, the different entities. For instance, entity is a door, or entity is a booking, or whatever, and certain characteristics. And then obviously the main diagonal is a self-reflective relationship, therefore we couldn't use it for anything. However, everywhere let's say, people will consider, the distance between them could be explicitly explained. And in the computation, only the upper triangle was used actually as an information source. So this sort of spatial feature representation matrix is a partly invariant, partly variant spatial information capturing means, and it was a structured representation, or is a structured representation of the spatial entities, their attributes. The attributes were included in the, let's say, the slots along the main diagonals, and also the relations. So the entities were clustered as person, exits, and files. This you can see here. I mentioned that the main diagonal in the computation was used as an attribute profile, and cells, every cells in the block of the upper triangular submatrix represented the attributes of the relationship. So because if there was a relationship here, then computationally it was specified that what were the observed characteristics, observed information, and the context information related to that. So this is how it works. And then obviously we have to work in time. But the matrix what I presented is just for one particular moment in time. But we just realized that if we multiplicate these and then we create a kind of hyper-matrix, so at every delta t we compute it, we can model the the continuity in the real life. There is one thing what we observe. If we for the sake of computation, we had large delta t's, which means that the follow-up computation of the next matrix started very long time. Maybe the physical process was finished in that delta t, so we couldn't capture that one. So it was a kind of challenge to set the computational delta t to the physical delta t. So the computational change detection to the physical change detection. This is obviously the continuous timing and the digital timing problem. So we combine these sort of feature matrices in a linear array, which were temporally interlaced, in a sense, time sequence. So we could monitor every time what is happening, and when something was observed here as a danger or whatever, immediately that this information was sent to the strategic planning, and the result of the strategic planner was sent to the communication unit. So, as I mentioned, at every given delta t increments, it was recomputed, and obviously it needed a lot of computation to do it, because, for instance, we considered first 10 times 10, then 100 times 100, and then 1,000 times 1,000 and elements for one matrix, and we had 100 matrix calculated. This was an enormous computational load. So I briefly mentioned that the size of the delta t, talking about the computational data, is strongly depend on the process, on the physical process, and for this reason, it is a kind of process resolution manner. So the corresponding cells and the temporary logically sequence matrices indicate the trends of changes. The concrete changes had to be extracted from the matrix. The computational was completed in a kind of real-time change evaluation, and we were actually very lucky because this based on this matrix, we could detect where the changes were. So it meant that not the whole matrix had to be recomputed, only those elements of the matrix which indeed change. And this way we could make it a kind of quasi real-time computational process. Then the next thing is the issue of inferring from the context information. As I mentioned, we detected or we recorded the space coordinate of every entity, we recorded the time intervals, and we recorded the attributes and the change of the attributes, and then we started with the signals and data. These provided the signals and the data, and that was converted into information, that was converted into certain knowledge which was related to the actions, and then the intellect, the semantic information for the messages. So actually, if you see this, it is the traditional knowledge pyramid which contains integrations and at the same time abstractions. So both the integrations and the abstractions had to be realized in the reasoning mechanism. So the inferring process started with the states of the entities, and then it went further with the calculation of the change, and then the interpretation of the situations and making scenes of the situation. So these are the entities. Then we calculated, for instance, the distance between the time proportional distance changes between them, and then we could see where the people were if they were approaching each other and they were a danger of forming a jam in front of an exit or whatever these were all used. And then we had a situation which used the information here and a kind of rule that, okay, if the distance is changing this way, then do this. And all these were merged into an intelligence that, okay, there is a growing danger and really the messages should be generated for the people. So here is a figure, what I was talking about, explaining the logic of the dynamic context reasoning, what we invented for this particular purpose. And what was interesting, as you could see here, that we provided a possible restricted implementation of the abstraction. Because if that abstraction is not there, then we cannot go to the state descriptive data to the action plan, which is related to a particular scene, which was really the intelligence what the system obtained. So this was actually our major control engine in this particular case, which was based on these set of information and which progressed according to this sort of line that we see here. So we have here is the functional structure on the main function level of this particular system, and we developed 4 specific mechanisms, reasoning mechanisms, which included several tens or even hundreds of computational algorithms arranged in a purposeful way. So one mechanism was for information representation, the other one was for knowledge inferring, the other one was for action plan devising, and there was a message construction mechanism as well included, and they were interrelated, communicated, and worked in parallel. In this particular case, obviously, we couldn't make a fire in any building. We couldn't test it in real life. For this reason, we were restricted to simulation, and we modeled the faculty building of the Faculty of Industrial Design Engineering of the University of Dance University where we were located, and then we had a setup. Here are the exit entities, here are the people, and here was a kitchen part, and our assumption was that the fire breaks out in the kitchen, and this is what we tried to model. Here is, sorry, it's still computing. Oh, I will not be able to show it because actually I wanted to show the computation with the system. I apologize for this. So it has been in the meantime computed, and now they are coming up. Yes. So this is how the fire proliferates. This is what in the simulated environment the people did. This is when the fire had a kind of advanced stage, but this is how the people could approach the existing exits and how they form jam and what happened this way. So when this was, sorry, I have to mention, I apologize for this mistake. This was without informing. But when we use the mobile phone for informing the people, this was the situation what we could achieve. So you can see a intensity increase. So you can observe here a slower proliferation of the fire, more intense and more rational move of the people, and they accessed and they were behaving more patiently and reliably nearby the exits, and they could be even informed to consider other exits as well. So this is how it works. So as you can compare it with the previous, sorry, if you can compare it with the previous slide, much less individuals was left in that. So this is the whole, this is what we did, and some takeaways. So the second example is also a good representation of the need for dynamic control regime when the traditional control techniques are not possible. Tomorrow I will show you a different exam for a completely different field where the traditional control mechanisms are not working. You could see that what we mean by system level reasoning, learning, and adaptation. Here, you could see that what we thought about the services which were rehabilitation services or informing services, but there can be also transformative services in different systems. We always try to validate that the novel system either are working or not. And obviously, we also proved that smart technology integration was a necessity in every particular case. And we also came to the conclusion that along this line and moving into the future of cyber-physical systems, we can address different challenges and can have different opportunities. I suggest you to look into the other colleague. Unfortunately, I missed to introduce him. He was Yong-Chun Lee, who worked with me and the research group. And one of the most important thing is this paper, Conceptualization of a real-time information processing platform for context-aware informing system. We also wrote a paper jointly about how to construct personalized messages, for instance, based on dynamic context information processing. Then there was a paper presented on dynamic computation of time varying spatial context. And then also I suggested study this paper, which is about underpinning theory and approach to applicable testing of constructive computational mechanisms. So this concludes the second lecture. In the first group, you have heard about the model-less control of smart systems. The second block presented informing CPS that utilizes dynamic context information management. So these may be triggering examples for you what sort of research and design efforts you can make. And see you tomorrow. But first of all, let's see if we have any question from you at the end of this today's presentation. Please, if you have any question related on or unrelated, I'm very pleased to answer it.
So, participant, any question from anybody? Any question? Any comment? If you don't want to question. Okay, then if no questions are there, I'll request once again to all of you to please switch on your cameras so that we can record attendance actually. Prashant Sharma, Keshav, Vivek, Arun, all of you please switch on your cameras.
Yes, sir, I switched on.
I'm not able to see your photograph.
Vineet, Sunil, and Jefferson. Vineet, Sunil, and Jefferson. No. Mithilesh also. Anyway. Okay then. I think Puneet, your mic is muted.
Sorry, I don't know what is happening. So once again, please switch on your cameras. I'll request two more people just. Jefferson, Sunil, and I can't still see Anil, Vivek, Arun, Ishant.
Sir, my camera is switched on.
Vivek, I could see you now. Anil, Arun, Ishant.
I have here, sir. My camera is switched on.
Okay now. Ishant.
सर ऑन है क्या?
अब बोलते हो तब ऑन हो रहा है. Anil, Abhineet.
Anil is on.
मेरे पे नहीं दिखा, मैं भी नहीं. Anil,
Vineet is not on. Jefferson and Sunil.
even Anil, I can't see. Anil, can you speak something? Actually, when you speak something, probably it becomes on. चलो ठीक है. So we'll take another short break, and in another 40 minutes time, at 4:30 sharp, we will restart the third session.
Let me thank you for all of you for the attention following the presentation, and I hope